Hello everyone, my name is Ireneo James Membrere, as stated, and I'm here to tell you about the first investigation of tripartite entanglement harvesting in the black hole vacuum. So this research was done in collaboration with Kensuke Gallic Yoshimura, Laura Henderson, and Robert Mann. 2 points in a quantum field are known to be entangled, and this entanglement depends on the space-time that the quantum field permeates. We can measure this using the entanglement harvesting protocol. So what this entails is multiple qubits locally interacting with a field, extracting correlations from the field, and becoming entangled. And so we measure the entanglement of these detectors as a proxy for the entanglement of the field itself. This is important to study because not only does it give us clues into fundamental physics problems, such as the origin of black hole entropy, but it also gets us one step closer to reconciling quantum mechanics and general relativity. A qubit is normally modeled by the UW detector. This is a two-level quantum system with a ground state and an excited state that models the light-matter interaction when angular momentum is conserved. Most of the research done so far has only looked at two detectors. For example, there was a study on two detectors in ADS. There was a study on two detectors in black hole spacetime, and they discovered the bipartite entanglement shadow. Basically, what this means is that when one of the detectors is too close to the event horizon, there's too much noise from the black hole, such as Hawking radiation, and this prevents the detectors from extracting any bipartite entanglement. And another study was rotating black holes amplifying entanglement. Comparatively little is known about multipartite entanglement. One exception would be a study done recently on 3 detectors in flat spacetime, and they discovered that you can harvest tripartite entanglement when bipartite entanglement is 0. So we asked the question, what happens to the entanglement shadow of a black hole when we introduce a third detector? We consider 3 static UDW detectors in a 2+1 dimensional BTZ black hole spacetime. The line element for this spacetime is given here. For the coordinates of the detectors, time, radius, and angle. L represents the ADS length. M represents the mass of the black hole, and the event horizon is given by the ADS length times the square root of the mass. We consider a quantum scalar field obeying this field equation, and so we can calculate the correlations of the field using the Whiteman function. Since BTZ is conformally equivalent to ADS, if we consider the black hole to be in thermal equilibrium with its exterior, then we can calculate the Whiteman function on BTZ as an image sum of Whiteman functions on ADS. The interaction between the detectors and the field is governed by this Hamiltonian here. Lambda represents the coupling strength. Chi represents the switching function, so it controls whether the interaction is on or off. Tau is a proper time. Sigma is the width of the switching function. We have our lowering and raising operators. And omega represents the energy gap between the ground state and the excited state of our detector. We initially start with the detectors in their ground state and the field in its vacuum state. And then we can use the time evolution operator to calculate the final state. But for a small lambda parameter, we can do a Dyson series expansion of the time evolution operator, truncate to a few terms, and calculate that final state explicitly. We trace out the field to get the final state of our 3-detector system in this basis, where the matrix elements P represents the transition probability of one of the detectors, C represents the local correlations between the 2 detectors, and X represents the non-local correlations. To measure entanglement, we look at a couple things. The negativity of entanglement is defined using the trace norm on a reduced state partially transposed. This is equivalent to taking the negative eigenvalues and adding their magnitudes for this reduced state. In 2x2 systems, the negativity is positive if and only if the 2 systems are entangled. So the negativity of entanglement exactly quantifies bipartite entanglement. The pi tangle, defined here as a various sum of differences of squares for negativities, exactly quantifies tripartite entanglement, but only for pure states. In a more general case, we can only treat the pi tangle as a lower bound. So this means that a positive pi tangle means that we are genuinely extracting tripartite entanglement, but a pi tangle of 0 or a negative pi tangle means that the results are inconclusive. The first configuration we consider are the detectors in an equilateral triangle around the event horizon of the black hole. We use identical detectors, so the coupling strength, the switching function, and the energy gap are all set equal to each other for the detectors. This is for mathematical simplicity. And for the following parameters in a Gaussian switching function, here we plot the negativity between any two pairs of the detectors and the pi tangle as a function of the black hole mass and the distance from the horizon. Looking at the negativity, we see that as the detectors approach the horizon, the negativity goes down to 0. This is, again, the bipartite shadow that we talked about earlier that was discovered in one of the previous papers. Looking at the pi tangle, we see that the pi tangle is positive at larger masses and longer distances as compared to the negativity. This region where the pi tangle is positive and we have no bipartite entanglement is a case of GHZ type entanglement. For the triangle configuration, we also considered other parameters. Here in the plot, we considered the energy gap varying and the distance. And we again found a region where we can harvest genuine tripartite entanglement. We looked at the ADS length, which looked very similar to the density plot shown in the last slide. And we also calculated the pi tangle for different boundary conditions, such as von Neumann or transparent. And it was very qualitatively similar to what we already have shown in the slides. But for all cases of the triangle, the pi tangle is only positive in a very small region of the parameter space. So as far as we know, it's relatively difficult to harvest tripartite entanglement when your detectors are arranged in this configuration. The second configuration we considered were the detectors on a straight line with the center of the horizon. The distance between A, B, and BC is fixed and set to be equal, and all three detectors move as one unit closer or farther away from the horizon. Here we plot the pi tangle as a function of the distance from the horizon for varying energy gaps. And we see that when we make the energy gap large enough, then the entanglement shadow of the pi tangle completely disappears. So this means that when, for a large enough energy gap, A can get arbitrarily close to the horizon, and we are still able to harvest tripartite entanglement. This actually happens within the bipartite shadow, and we can see that explicitly. So in the bottom plot, we plot the various negativities for an energy gap of 0.01. And looking at the bipartite negativities, they're all 0 from about the horizon to 0.6. But the pi tangle is positive between 0.2 and 0.6. So this region between 0.2 and 0.6 sigma is where we can harvest this GHZ type entanglement. The pi tangle also asymptotes to a constant value as the distance gets to infinity. And this is expected because BTZ is asymptotically ADS. And in contrast to the triangle case, majority of the parameter space for the line yields a positive pi tangle. And so it's relatively easy to harvest tripartite entanglement when our detectors are arranged on a line. We consider the line again, but for larger detector spacings. So at a detector spacing of about 5 sigma, the detectors are nearly causally disconnected. Here we again plot the pi tangle as a function of the distance from the horizon. And what we see this time is that the pi tangle has a spike near the horizon larger than the asymptote. And this spike occurs within the bipartite shadow, as we see below, looking at the negativities again. The spike also occurs in the tripartite negativities. So where is this spike coming from? Here we plot the matrix elements, P, C, and X, versus the distance. And one is able to calculate the negativities as direct functions of these matrix elements, P, C, and X. So looking at any of the correlation elements, C or X, involving the detector A, we see that these elements have maxima near the horizon. And it's these maxima that are responsible for the spike in our tripartite negativities, and thus the spike in the pi tangle. We can also calculate the bipartite negativities as direct functions of P, C, and X. And NAB, NAC both have a negative PA term. Looking at the transition probability here, PA is extremely large near the horizon, driving these to 0, and the high transition probability of detector A is what's actually responsible for the bipartite shadow that we see. In summary, we looked at the tripartite entanglement harvesting protocol for 3 UDW detectors in a BTZ black hole spacetime. We looked at an equilateral triangle configuration where we found that we could harvest tripartite entanglement at larger masses and longer distances as compared to bipartite entanglement. We saw the bipartite shadow for the triangle case, and we also found that only a small region of the parameter space guaranteed us the ability to harvest tripartite entanglement for our triangle configuration. We also looked at a straight line configuration, and in this case we found for a detector separation of 1 sigma that we can drive the energy gap large enough in order to eliminate the entanglement shadow in our tripartite entanglement. We found that at larger detector separations of 5 sigma, there is a near horizon spike in the pi tangle, which comes from the pairwise correlations overcoming the noise near the event horizon. And we also found, in contrast to the triangle case, that the majority of the parameter space allows us to harvest entanglement in the line configuration. An interesting avenue for future research would be to classify the harvested entanglement into the categories of GHZ, W, biseparable, and fully separable states. Thank you for listening to my talk. If you want any more information, please see our publication.